In this video, we're going to explore exponential functions, which will be a new function for us in this course at least. We're going to evaluate exponential functions, graph them, define the number e, which is a common base for exponential functions, and solve some basic exponential equations. We'll solve more complicated exponential equations in a later video where that's the focus of the video. So first we'll start again with a definition of what an exponential function is. And the definition says that an exponential function is a function of the form f of x equals some constant, we'll call it c, times a, that number a is called the base, raised to the power x. So what you want to notice is the variable is in the exponent, and like I said, a is called the base, and that is the growth factor, and c is the initial value. Let's look at why that would be the case. The initial value would be when x is 0, and if we put x equals 0 in, we would have c times a to the 0. A to the 0 is just 1, so we'll have c times 1, which is c. So when x is 0 at the initial point, the value is c. Oftentimes these functions are modeling where the input is time, so the initial time being 0 oftentimes makes sense. So the domain is all real numbers, and we'll talk about why here. Any number, we can put the exponent any value in for x, and that will make sense. So a to any power is defined just fine, so the domain would be all real numbers. We will talk eventually about why a would need to be positive and why we don't want a to be 1, and why we wouldn't want c to be 0. That one's pretty obvious. If c is 0, we would just have 0 times a to the x, which would always be 0. And if a is 1, 1 to any power is always going to be 1, so that would not be very interesting either. So we'll talk eventually about why a should be positive only, but we'll save that for a little bit. So again, the variable is in the exponent. That's what makes it an exponential function. It's different from x squared, where there is an exponent, but it's a constant exponent of 2. So here we have an exponent that's changing as x changes. So we're going to start with the graphs of some basic exponential functions. F of x equals 2 to the x. Notice in this case we could write this as f of x equals 1 times 2 to the x. So the initial value would be just 1 when x equals 0. Let's make a chart of x and y values for this graph, but we're not going to do that for long. We'll have a better way. So we'll pick some x values and then we'll evaluate the function 2 to the x for these x's. Let's do -3, -2, -1, 0, 1, and 2, just to get a start at least. 2 to the -3, remember a negative exponent does a reciprocal, so that would be 1 over 2 to the 3rd, so 1/8. 2 to the -2 would be 1 over 2 squared, which would be 1/4. 2 to the -1 would be 1 over 2 to the 1, which would be 1/2. 2 to the 0, anything to the 0 is defined to be 1. 2 to the 1 is just 2, and 2 to the 2 is just 4. Alright, so let's plot those points. We have -3, 1/8. It's hard to be very precise about that, but then we have -2, 1/4 would be slightly bigger, well, twice as big. -1, 1/2. 0, 1, 1, 2, 2, 4, and then we would have 3, 2 cubed, which is 8, and this is going to start growing really quickly. When I have x equals 4, I'd be to 16, and we'll be off that graph. Off the grid, sorry. So it's going to grow quickly, and that's where the term growing exponentially comes from. From a function like this, it will grow and grow and grow very, very quickly. So over to the left, we want to know what's going on. And for larger and larger negative values, we'll have 1 over a larger and larger denominator. So as x goes to negative infinity, the fractions are going to get smaller and smaller because the denominators are going to get larger and larger. So we'll say y goes to 0, but doesn't ever get to 0 because we always have 1 over that denominator. And as x gets larger in the positive direction, y will be unbounded as well in the positive direction. So this will go higher and higher, but we're never going to get to 0 on the left side of the graph. You can see that the y-intercept would be 0, 1 for this graph. The x-intercept will be none because that graph's not going to cross the x-axis. The domain is all reals. It's going to stretch left and right without bound. The range would be as low as 0, or as close to 0 as we can get, but we're not going to ever hit 0. And what I call the key points are right here in the middle of the graph, where it's not incredibly steep, but it's also not nearly horizontal. And those come from these 3 points that I highlighted right there. So the key points, I would say, are negative 1, 1/2, 0, 1, and 1, 2. Because on those points we can see where the graph has its turn that's not super steep, but it's also not flat, like I was saying. The horizontal asymptote is a horizontal line that we don't cross, we get closer and closer to. So in this case, that would be the x-axis, or y equals 0. Notice also that we've got an interval of increase. From negative infinity to infinity. It's always increasing, right? And in the previous video, we talked about a function that's always increasing has to have an inverse because it's 1 to 1. So we will eventually talk about the inverse of this function. The next one, f of x equals 1/2 to the x. Let's do the same thing. Let's look at making a chart of x and y values. But we'll abandon this process soon. This time y is 1/2 to the x. So we've got, let's do negative 3, negative 2, negative 1, 0, 1, and 2 again. This time when we have x equals negative 3, we have 1/2 to the negative 3. So we do a reciprocal, which gives us 2 instead of 1/2. And we do 2 to the 3rd, which should be 8. And 1/2 to the negative 2, do the reciprocal first, so that's 2 squared would be 4. 1/2 to the negative 1 would be 2 to the 1, or 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 to the 2nd is 1/4. So, plotting these points, we have negative 3, 8, negative 2, 4, negative 1, 2, 0, 1, 1, 1/2, and 2, 1/4. So we can see this graph is rising as we go to the left, because if we do the reciprocal of 1/2 and then put a larger and larger value a larger and larger value in the negative sense. The reciprocal would be a large value in the positive sense. So growing as we go to the left and shrinking as we go to the right. A higher and higher power on 1/2 is just going to get smaller and smaller, but it will never get to 0. So just like in the other one, the x-intercept there would be none because y is never going to be 0. The y-intercept would be 0 for x, 1 for y. The domain is all reals because there's not a left or a right bound. And the range would be 0, not including 0 to infinity. And our key points are going to be right in this interval again. So we're going to take, with x values -1 and 0 and 1, the y values are different this time, but what I'm really interested in is keeping these x values for my key points. This time if I put -1 on, we had 2, and then when x was 0 we have 1, and when x is 1 we had a half. Notice this pattern. 1/2 was the base. We always get 1 when the exponent is 0, and 2 is the reciprocal of the base. Which is the same as what we saw in the previous example. In that one, when x was -1, we got a half. That's the reciprocal of the base, which was 2. And when x was 1, we got 2, which was the base. Horizontal asymptote at y equals 0. And this time, we have an interval of decrease from -infinity to infinity. The function's always decreasing instead of always increasing. One thing you can notice is that if y equals 1/2 to the x, that's the same as 2 to the -1 to the x, which is the same then as 2 to the -x, which is just y equals 2 to the x reflected across the y-axis. So if you compare the graph that we just did with this graph, they're the same, but reflected over the y-axis, because we made the x's opposite. So let's write down some general ideas here. The graph of b to the x, as long as b is positive and b isn't 1, is going to have x-intercept none, because we're never going to cross the x-axis. The y-intercept would be when we put 0 on for the exponent, we'll get 1 for the expression. The domain should be all reals. The range should be 0, not including 0 to infinity. The points I want to track would be -1, the reciprocal of the base for y, 0 for x, 1 for y, 1 for x, and the base for y. And there will be a horizontal asymptote on the x-axis, which is y equals 0. So we'll look at a few more of these, or maybe just one more of these that doesn't include any shifting or anything like that, and then we'll start applying shifts and stretches and compressions to this general graph. So first, f of x equals 3 to the x. This is going to be another one in our family of functions that we can apply transformations to. So the base is 3 in this. The y-intercept will be 0, 1. There will be no x-intercepts. The domain will be all real numbers. The range will be 0 to infinity. And then the points, we want -1, reciprocal of the base would be a third, 0, 1, and then 1, and the base is 3. We could list other points as well, but those are the nice points where we've got those most uh, most telling, maybe, curve of the graph. The horizontal asymptote will be at y equals 0. So if we plot these 3 points, that'll give us an idea of whether the graph is sloping upward to the right or coming down from the left. So -1, 1/3, 0, 1, 1, 3. And we can see it's sloping upward to the right. And anytime the base is bigger than 1, that's what should happen, because that should represent exponential growth if we have a factor that's bigger than 1 that we're multiplying by itself over and over and over. So since this base is bigger than 1, we should expect to see it going upward to the right, or increasing always. We would have 9 when x equals 2, and then to the left we're just going to be getting smaller and smaller and smaller and smaller. We shouldn't get to the x-axis, but it's hard to make that obvious on my graph here. And we can write the interval of increase all reals because it's always increasing. And remember, those are x intervals, not y intervals. All right, then f of x equals 1/3 to the x. One more just kind of basic one, and then we'll start doing some that are more interesting. So y-intercept x is 0, y is 1. X-intercept, none. Domain, all reals. Range, 0 and larger, but not equal to 0. Points, take your x to be -1 and 0 and 1. The y's are then the reciprocal of the base, which would be 3. 1 when x is 0, and the base, which is 1/3 when x is 1. Horizontal asymptote will be y equals 0, unless there's any shifting, which there's not. And we're expecting, because the base is between 0 and 1, that the graph is going to be decreasing. As x gets larger, we're taking more factors of a third. So that's going to get smaller and smaller and smaller. So -1, 3, 0, 1, 1, 1/3. -2, we would have 9, right? It's just going to get larger in that direction. There. Okay, now we want to see what happens if we involve some transformations as well. So here what we want to think about is we can see that there's an exponential function at the heart of this, because I have an x up in the exponent. So when I think about the parent, it's going to be y equals and just the base with the exponent x. Everything else is going to be thought of as a transformation, but the base has to be part of that parent function. So I want 3 as the base with the exponent x. The negative sign will be part of the transformation, and the +2 will be part of the transformations. So on my parent graph, I would have -1 and 0 and 1 for my x's that I'm going to track. 1/3 for the y, and then 1, and then 3. And then my transformations, I have a -1 times, let's look at it this way, the function, and then I'm adding 2. If I'm multiplying by -1, that's a reflection across the x-axis, because I'm changing my outputs. If I were changing my inputs, the negative would be up by the x. So I'm changing my y values. I'm multiplying out the y values of the outputs by -1. So that's a reflection across the x-axis, and then a shift up 2. So when I track my points, I'll reflect across the x-axis first, and then I'll go up 2. So reflecting across the x-axis, I would have 1 and then negative 1/3, 0, negative 1, 1, negative 3. Up 2, that's going to leave me at negative 1, 1 and 2/3, then 0, 1, and 1, negative 1. So my final graph is going to look like negative 1, 1 and 2/3, 0, 1, and then 1, negative 1. I want to think about the horizontal asymptote too before I sketch in the rest of the graph. I don't want to cross the horizontal asymptote. Because of this shift up 2 units, what normally would have been y equals 0 is going to shift to y equals 2. Anytime there's a vertical shift like that, like we have this +2, or if we had -3, that will be the horizontal asymptote location. So in this case, like I said, we'll have y equals 2 for the horizontal asymptote. So I want to sketch that in before I complete the rest of this graph, so that I know to get closer and closer to that line. So I can see I'm going to be coming upward, getting closer to that line, and then the other side, I'm just, it's going to be falling off really quickly. We could be more accurate about points, but this is good enough. I've got my 3 points listed, the transformations applied to my original key points, and I've got the horizontal asymptote in the right place. So the domain for this would be still all reals. That's not going to change. The range will be different, obviously, with this reflection and the shift. It looks like it should be negative infinity to +2, still not including +2. And it looks like we have an interval of decrease. Of negative infinity to infinity. These functions will always be either entirely increasing or entirely decreasing, and obviously in this case it's decreasing all the time. One more using transformations to sketch. This time, instead of having a reflection, we have an x minus 1 in the exponent. X minus 1, that's adjusting the x values. So again, our parent, we can see we have something exponential here. We just want y equals the base to the x, which in this case is 3 to the x. And then this x minus 1, that's going to be a shift to the right. And then the +2 again will be a shift up 2. As you can probably hear, it's 4th of July. All right. So y equals 3 to the x, our key points. Negative 1, 1/3, 0, 1, and 1, 3. And then our transformations, we want to go right 1 and up 2. So right 1 is going to give us 0, 1/3, and 1, 1, and 2, 3. All the x's go up by 1. Up 2 is going to give us 0, 2 1/3, 1, 3, and 2, 5. And also we want to keep track of that horizontal asymptote, which is always the same as the vertical shift. So y equals 2 in this case. So let's put that in. And then let's plot these other points. So 0, 2 1/3, 1, 3, 2, 5. the domain, all reals, the range, looks like we don't go any lower than 2 and we don't get to 2, so 2 to infinity, and the interval of increase is all reals, negative infinity to infinity, and it's never decreasing, just always increasing. The next thing we want to talk about is this constant e that's similar to the constant pi, and that it's called what's called a transcendental number. It goes on and doesn't repeat. It doesn't terminate, doesn't repeat, just goes on forever. So rather than using an approximation for this number, we just write it as a symbol, and the symbol we use is e for Euler's constant. So the number e happens to work well as a base for population growth that's unbounded or continuously compounded interest models. At least those are two situations where this number e arrives naturally. So this is used as a base in what's called the natural logarithm, and you'll also just see it's called the natural exponential function if e is the base in that exponential function. The way it's defined is the limit as n goes to infinity of this expression 1 plus 1 over n raised to the nth power. This is new notation to us. Limit as n goes to infinity, it's something that comes up in calculus, and you'll get to that eventually if you take a calculus class, but it means as n gets larger and larger without bound. Whatever happens to the expression, whatever it gets closer and closer to, is what we call e. So that's what it says here. That means that e is the value of this expression as we take larger and larger values for n. So let's grab your calculator. Sorry, I didn't have this set up. And let's put that expression in, the 1 plus 1 over x to the x. Let's put that in for our y equals. And then let's look at our table. Notice for what I've got right here, it says if x is 0, I have an error. But we've got x equals 7, 8, 9. We can see these are just growing, and they're still growing, still growing, still growing a little bit. Let's go to table set again. And let's start at 1, we'll start at 10 and we'll go up by 10s. So you can see these are still increasing slightly, but they're only increasing out in the hundredths place at this point. The thousandths place. The hundredths place is staying pretty steady. Still increasing in the thousandths place. Just scrolling down. But nothing's changing too much. They're still changing in the 10,000ths place, it looks like. Let's do this. Let's do table set again. Let's start at 1,000, and go up by 1,000. So at 1,000, 2,000, you can see these are still changing a little bit, but now they're just going to be stuck there. So at least out to 4 decimal places, we can see we have about 2.7182. Take a snapshot of that. Can't have it quite this big, but there we go. So we can see that we get approximately 2.7182. And we truncated that, we cut it off, so that's not the exact value for E, but it's close as an approximation, right? If you grab your calculator again, you'll notice that there is an E button on your calculator above the division symbol if you have a TI-83 at least, or 84, above the division symbol. So if you do second and then the division symbol and hit enter, you'll get a slightly better approximation that looks like it might almost repeat, but it actually doesn't. It doesn't continue that pattern. Or if you don't have just an E button, you could also you definitely have an E to the X button. And if you wanted to get just what's E, you would put E to the 1 and hit enter. So one of those should be an option for you. And you should get that. All right. So if I want to sketch the graph of e to the x, I can't be, incredibly accurate, but I can at least get a good approximation of it. So my key points, I want to keep my x values as -1 and 0 and 1. Then I'd have 1 over e and 1 and e as my y values for those x values. Keep in mind that 1 over e is between, what, a half and a third? And e is like, we'll just say 2.7. Good enough for our graph. So -1, something between a half and a third, 0, 1, and then 1, 2.7. Fine. That's as accurate as we need to be. The domain would be all reals. The range would be 0 to infinity, not including 0. And there would be a horizontal asymptote at y equals 0. And it's always increasing. And then, one with some transformations, e to the -x plus 1, my parent, I can see it's exponential, so I just want y equals the base, which is e to the x. Choose your x's to be -1 and 0 and 1. Then I would have on my parent function 1 over e again, 1 and e as the y values. The transformations I have this time would be, I'm multiplying the x by -1, so reflect across the y-axis. Change the x's, and then go up 1. So, reflecting across the y-axis, make my x opposite. That doesn't change that middle point. -1e for the last one, and then up 1 would be 1, 1 plus 1 over e, 0, 2, and then -1, 1 plus e. Because of the plus 1 on the end, I know my horizontal asymptote will be shifted up 1. So it'll be at y equals 1 instead of y equals 0. So let's graph that right away. And then the others, we had 1, 1 plus a half and a third, or half between a half and a third, 0, 2, and then -1, 1 plus e, so like 3.7 roughly. Domain, all reals. range looks like 1 to infinity, not including 1. And we have interval of decrease from negative infinity to infinity. I think that's just about the end of the graphing here. Let's take a look at the next page. The rest of the graphing will be mostly on our calculator. So here what we've got is asking us to find the solutions of 3 to the x equals x to the 4th using your graphing calculator. And no matter how much math you take, you're not going to have a better approach than an approximate solution on your graphing calculator to something like this. When we have a mixture of exponential and polynomial equations like this, there's not a better approach than just an approximate solution using some numerical methods or your calculator. So let's do this. Let's graph both sides. First, let's think about what this graph is going to look like. And then we'll grab our calculators. But when x equals 0, 3 to the x is going to be at 1. I'll do that one in black. And x to the 4th is going to be at 0. Right? When x equals 1, 3 to the x is going to be at 3. And x to the 4th is going to be at 1. When x is negative 1, now 3 to the x is at a third, and x to the 4th is at positive 1. And as we go left, we know x to the 4th is going to get larger and larger, but 3 to the x is going to get closer and closer to the x-axis. So we know what that side's going to look like. What we're also going to see is that somewhere here, x to the 4th is going to get higher than 3 to the x, just for a moment. But we know that in the long run, an exponential function always will outpace or grow quicker than a polynomial function. So there's no way that 3 to the x can stay underneath x to the 4th for its graph. So when we go look at this on our graphing calculator, whoops, we can graph these two functions, 3 to the x and x to the 4th. We can just look in our standard window first, and we can see just what I was indicating here. We can see in the standard window there are two intersection points. Let me just change that window a little bit. I'm just going to do negative 5 to 5 even for the x's. I'll take a picture of that. So we need to see more. to the right to find another intersection point. Because they have to switch places again. There's no way that this 3 to the x is going to stay underneath that graph of x to the 4th. So first let's find these two intersection points. Intersect. First curve, fine. Second curve, fine. I'll guess -1. And then we get -0.8022 and then 0.414 for y. So one of them is approximately x equals -0.8022. And then the next curve looks like it's maybe over somewhere by 2, so I'll do my guess as 2. And it's telling me 1.517 roughly. And there has to be another intersection point somewhere out here past x equals 1.5. So I'm going to do window x equals, I'm going to do 1 to 10. And then I'm going to try a zoom fit. I don't know if that's going to help us or not, but that'll adjust the y values for those given x values. And that actually doesn't work too badly. Let's adjust it so that we're not seeing it. It looks like it's up here close to where we were. Actually, what do we do? 1 to 10? We're already seeing that one. Did I really do a zoom fit? Let's try that again. Okay, now we can see it, that it's out here somewhere. So I'm going to change my window so that instead of 1 to 10, we're maybe like, I don't know, 5 to 8. So let's do 5 to 8, and then a zoom fit. And then we can see it pretty well. So we'll go second, calculate, intersect, first curve, enter, second curve, enter, guess, we'll just enter, and it looks like it's about 7.17 roughly. So copy that. And what we also use then is this picture. And we did x min 5, x max 8, and a zoom fit to get to that image. So the last one, it looks like x is about 7.17 roughly. So we get 3 solutions. In example 3, we have what's called a logistic growth model. So rather than having unbounded population growth, many populations follow a logistic growth model, which has the general pattern that has this sort of S shape, where we've got what's called a carrying capacity, the level that when reached, where the population starts to level out. So this bird species follows this logistic growth model where T is in years. First, we're asked to find the initial bird population. Initial would be when time equals 0. So we want to let t be 0, so n of 0. We would have 5,600 divided by 0.5 plus 2.75, oh no, 27.5, sorry about that, times e to the 0, which is 1. So 5,600 divided by 28. That would be 200 because 56 divided by 28 is 2, so 200. So the initial population would be 200 birds. Graph the function using your graphing calculator. Let's see. So if we put that in, we've got 5,600 divided by 0.5 plus 27.5 e to the negative 0.044x. And we want that all in parentheses. So one set of parentheses around the whole denominator, and then another just around that exponent. And then our window, we want time to be positive, so I'll take x to be 0, and then let's go out to maybe, I don't know, 100 years, and the scale being 10. And then let's do a zoom fit to get the y's that we want. Looks like we don't see the population leveling off there yet, so let's go a little further than 100. Let's go to 200 and see if that's better. Try another zoom fit. Now we're starting to see it level off. Let's go even, let's 100 more, so 300. And we'll do x scale 30. There we can see it and starting to level off. Try zoom fit again. So there's a decent graph, and it took us a while to get to that, but knowing what we were expecting for logistic growth, we wanted to see it sort of start to level off at the carrying capacity. And let's take a picture of that. And what we did to get this was we had x min 0 and x max 300 eventually, and then we did a zoom fit to get the y values to show up correctly. So there's our graph. What sizes the population seem to approach as time goes on. We can either just trace along this graph, or we can look at the table and we can see for large values of x, all these y's are at 11,200. So I would say it looks like we're approaching 11,200. So based on that table, we're going to level off at 11,200 birds. When will the population be 7,000 birds? We want to do y1 equals our function, which is a function of x rather than t, and y2 equals 7,000, and intersect. So we'll have a line, through here at 7,000 and figure out where that intersects. So let's do that. Find the intersection point, so option 5. Looks like about 102.69. So approximately 102.7 years. And again, this 11,200 is called the carrying capacity. And notice also that we can get that from the formula. As t gets large, that exponent on e is getting huge in the negative direction. So 27.5 e to the negative 0.044t is going to go to 0 because it'll have a large negative exponent. So the carrying capacity is basically coming from 5,600 divided by 0.5, which is the same as 5,600 times 2. So we can see where that 11,200 is coming from. Example 4 is asking us to come up with an exponential function that fits a given set of data. And here what we can see is that we have 0, 3 as one point. We have to see that from the graph. And then we're given 1, 1/6 as another point. So we know that f of 0 is 3. And we also know that f of 1 is 1/6. And we need to find c, the initial value, and a, the base. So what we know is that c times a to the 0 is 3, filling in x equals 0 into our pattern. And we know that c times a to the 1 is 1/6. So what we have is basically a fairly simple system of equations. A to the 0 is just 1, so this is c times 1 equals 3, or c equals 3. And then we can plug that into the other, and we have 3 times a equals 1/6, which means a is going to be 1/6 divided by 3, or 1/18. So our function is 1/18 as the base and 3 as the initial value. So f would be 3 times 1/18 to the x. Notice that you don't want to multiply the 3 and the 1/18 together because that would be changing the base. The base needs to stay as 1/18, but 3 is just basically like a vertical stretch factor. It's all being multiplied by 3. You can do this, the process we just went through, as long as you have 2 points given on the exponential graph. You can set up a system of equations and solve that system for c and for a. The next thing we're going to do is look at solving some really basic exponential equations. We will have more comprehensive methods for solving exponential equations soon, but at this point, the best we can hope for is that we have an exponential equation where both sides can be expressed in terms of the same base. So our technique is going to be express both sides as exponential expressions with the same base. And then if we have the same base on both sides, we can equate the exponents. And we'll see that in a second. So in example 5a, we have on the left side, obviously the base is 5 and the exponent is x plus 4. We want to be able to write 1/25 as 5 to a power, and that's a reciprocal, so we know that the exponent is going to be negative. 5 squared is 25, so that would be 5 to the negative 2. Since the bases match, the exponents must be equal. So it's not that we're going to divide by 5 or cancel the 5's out. We're just saying because the bases are the same, the exponents have to be the same. So x plus 4 has to be negative 2, which means x has to be negative 6. So again, don't divide by 5, just make some statement like this. Since the bases are the same, the exponents have to be the same. Similarly, on the next one, we can say, well, this would be e to the 4x times e to the x squared equals e to the 12th. Then e, if we have the base the same, we can add these exponents, x squared plus 4x. And then the bases are the same, so the exponents must be equal. Which means x squared plus 4x has to be 12. So we have a quadratic equation here to solve. We can try to get a 0 and factor, which will work. X plus 6, x minus 2. So either x is negative 6 or x is 2. So that one happens to have two solutions. But again, in this particular video, all we're going to be able to do is solve exponential equations if both sides can be written in terms of the same base. The next example here is trying to get at the difference between the growth of a linear function and the growth of an exponential function. And what we want to do is compare the average rate of change on intervals of length 1. So the average rate of change between x equals negative 1 to x equals 0, we have the change in y's, so 1 minus negative 2, over the change in x's, 0 minus negative 1. So that's just 3 over 1, right? From x equals 0 to x equals 1, again, just tracking that average rate of change for the first function, we have 4 minus 1 over 1 minus 0, so again, 3 over 1. And between 1 and 2, the average rate of change, change in y over change in x, we've got 3 over 1. 7 minus 4 over 2 minus 1. So in this case, the average rate of change is constant. Anytime we see that, what we have is a linear function. So anytime the average rate of change is linear or constant, the function is linear. Then the next one, the average rate of change from negative 1 to 0 we have 2 minus 1 over 0 minus negative 1. So 1 over 1, which is 1. The average rate of change between x equals 0 and x equals 1. Again, we're always tracking change in y over change in x. So we're going to have 5 minus 2 over 1 minus 0, which is 3. So we can see the average rate of change isn't constant in this one. Let's take a look at the next one. Looks like 7. So we went from 1 to 3 to 7. So it's definitely not linear, and it's also not increasing by a constant factor. If the function is going to be exponential, we know every time x goes up by 1, we increase by another factor of whatever the base is. So what we see is the average rate of change is not constant. So f is not linear. And also the average rate of change is not increasing by a common factor. So f is not exponential. So let's take a look at the last one. I should have said g instead of f. So g is not linear and g is not exponential. And then let's take a look at h. So the average rate of change between x equals negative 1 and x equals 0. We've got 5 minus 5 halves over 0 minus negative 1, so that would be 5 halves. X equals 0 to x equals 1. We've got change in y over change in x would be 10 minus 5 over 1 minus 0, so 5. And then x equals 1 to x equals 2. Change in y over the change in x there is going to be 20 minus 10 over 2 minus 1, so 10 over 1. This time we doubled on the first interval and then doubled again on the second interval. So in this case, the average rate of change is increasing by a factor of 2. Over each 1 unit interval. Which means the function h is exponential with base 2. So if you see over each 1 unit interval the average rate of change increasing by a constant factor, then we know that's an exponential function, and that constant factor is the base of the exponential function. And back when we had a constant average rate of change, we said it was a linear function, and that rate of change would be the slope. So we have slope 3 for that first function. One more application here. It says between 5 and 6 p.m., cars arrive at Jiffy Lube at the rate of 9 cars per hour or 0.15 cars per minute. The following formula from probability can be used to determine the probability that a car will arrive within t minutes of 5 p.m. So we see we've got an exponential function with it's got a negative coefficient on t. So it says determine the probability that a car will arrive within 15 minutes of 5 p.m. So it said within t minutes of 5 p.m. So this would be my t value. So that a car is going to arrive somewhere between 5 o'clock and 5:15 p.m. So I do f of 15, 1 minus e to the negative 0.15 times 15. Lots of 15s there. And you'd need a calculator for that. So I'll do 1 minus e to the, and then we want to make sure we get all this in parentheses, so negative 0.15 times 15. So 0.8946. Or 89.46%. So there's that percent chance that a car will arrive between 5 and 5:15. Determine the probability that at least one car will arrive within 30 minutes of 5 p.m., so before 5:30. So we were looking for f of 30 in this case. 1 minus e to the negative 0.15 times 30. And I'm thinking that we might as well put this into our graph here. So 1 minus e to the negative 0.15x. And let's go to the graph. Let's do window here first. We're thinking x between 0 and 60, it looks like. Scale of 1. And we're talking probabilities, so let's do 0 to 1. Get a graph. All right. And we want to know when x is 30. So let's do evaluate. When x is 30, we get 0.9888891. All right. And then what? I just want to make sure I entered that correctly. That seems like a large probability. 1 minus e to the negative 0.15 times x. Yep, I did. What value does f approach as t becomes unbounded in the positive direction? Well, we can see, we're looking at this. If t is large and positive, then the exponent is large and negative. So e to the negative 0.15t would go to 0. It's going to get smaller and smaller and smaller. So f of t would approach 1. We already have a graph of f, and we want to figure out how many minutes are needed to reach 60% probability. So we would do like our y2 equals 0.6 and intersect. First curve, enter. Second curve, enter. Guess, just enter. Looks like about 6.1 minutes. Oops. All right, so hopefully that has you pretty comfortable with exponential functions. The next thing we're going to do is look at the inverse for the exponential function, which is called the logarithmic function.